Welcome to The Explainer. Today, we are diving deep into a technology that is jumping straight out of science fiction and into our reality, quantum computing. We're going to break down what it is, why it's suddenly all over the headlines, and what it really means for all of us.
All right, let's just jump right in with a number that completely changed the game, 3,000. Recently, researchers hit this massive milestone with a 3,000 qubit system. And you gotta understand, this isn't just another small step forward. No, this is a huge leap that has the entire tech world buzzing.
In fact, this breakthrough was so significant, it prompted NVIDIA's CEO, Jensen Huang, to flat out declare that we've hit a turning point. You know, just a few years ago, most people thought practical quantum computing was still decades away. But now, that timeline is shrinking fast. So, what is the big deal here?
So, this new powerhouse quantum computer came from a team up between Harvard, MIT, and a startup you might not have heard of called Quera. And they didn't just beat the old records from giants like IBM, they absolutely shattered them. And get this, it wasn't just about hitting 3,000 qubits. They kept the machine running stable for over 2 hours. That's a huge deal for stability. So, okay, let's get into what actually makes this tech so mind-bendingly different.
To really get the quantum revolution, we have to start with the absolute basics. At the very heart of it all is this fundamental jump from the classical bit that we all know to the much, much weirder quantum qubit.
Okay, so here's the core idea. Everything you use, your phone, your laptop, it all runs on bits. And a bit is simple, right? It's just a light switch. It's either on or it's off, a 1 or a 0. That's it. A qubit, though, well, a qubit plays by the bizarre rules of quantum mechanics. It can be a 1, a 0, or somehow both at the exact same time. And this is all thanks to a couple of really strange but incredibly powerful principles.
First up is superposition. The best way to think about it is like a spinning coin. While it's spinning in the air, is it heads or tails? Well, it's kind of in a state of being both, right? That's what a qubit does. And because of this, a small number of qubits can explore a massive number of possibilities all at once. So while 10 bits can store exactly one number, 10 qubits can store over 1,000 numbers simultaneously. That's where you get this insane parallel processing power. And if superposition sounded weird, get ready for entanglement. Einstein famously called this spooky action at a distance, and for good reason. When you entangle two qubits, they become linked. They're basically a single entity. If you measure one, you instantly know the state of the other one, even if it's on the other side of the planet. It's this spooky connection that lets quantum computers perform incredibly complex calculations that classical computers just can't. So here's the bottom line, the most important thing to remember. Quantum computers are not just faster versions of the laptops we have now. That's a huge misconception. They are a totally different kind of tool, built on the laws of quantum physics, designed to solve a specific class of problems that are literally impossible for even the world's best supercomputers. But to build something so out there, you need some seriously revolutionary hardware. So let's look at how they're actually building these things.
Okay, so that 3,000 qubit record we kick things off with, how did they actually pull it off? Well, the answer is in a specific technology called the neutral atom method, and it is seriously picking up steam in the quantum hardware race.
Now, this sounds like pure science fiction, but it's real. They use lasers that act like optical tweezers to literally grab and hold individual atoms in a perfect grid. The energy level of each atom then becomes a qubit. The huge advantage here is scalability. It's way easier to add more and more atoms. And, maybe most importantly, it doesn't need to be cooled to near absolute zero like some of the other methods. That's a game changer.
And this just shows you the horse race that's going on right now. You had the early pioneers like IBM and Google betting on superconducting qubits. They're super fast, but they have to be kept colder than deep space, which makes them incredibly complex and hard to scale. But these other methods, like neutral atoms, offer a different set of trade-offs. And right now, the neutral atom approach seems to have the clearest path forward to get to thousands and even millions of qubits, which is exactly why it's making all the headlines.
So, with this intense hardware race happening, you'd probably expect a computing giant like NVIDIA to be throwing everything they have at building their own quantum computer, right? Well, nope. They're playing a completely different and maybe much smarter game. They're using the classic picks and shovels strategy. You know, in a gold rush, sell the tools. It's a really pragmatic move. See, the thing is, for the foreseeable future, quantum computers aren't going to replace your laptop. They're specialist machines that will need to work hand in hand with classical supercomputers. The future isn't quantum or classical, it's quantum and classical working together. So NVIDIA's big bet is this. Instead of trying to build the one winning quantum computer, why not build the essential software bridge that all of them will need to talk to the classical world? And their strategy is laid out perfectly. First, they built Cuda-Q, which is this universal software platform that lets developers write code for these new hybrid systems. Second, they're pouring money into research centers to get the smartest people working together. And third, they're just straight up investing in the hardware companies themselves. They want to own the entire ecosystem that connects these two worlds. You can see it right here in their investments. They're not betting on just one horse to win. They've put money into companies using photons, trapped ions, and neutral atoms, all the leading approaches. They're hedging their bets, making sure that no matter which hardware technology wins the race, NVIDIA's platform will be absolutely essential. It's a brilliant move. So we have all this amazing progress, thousands of qubits and billions in investment. Where is this all actually going? Well, the truth is, the biggest challenge and the biggest rewards are still ahead of us. This brings us to the single biggest hurdle in the entire field. See, all those thousands of qubits we're celebrating, they're what we call physical qubits, and they have a huge problem. They are incredibly fragile. It's like trying to have a perfect quiet whisper in the middle of a rock concert. The slightest little thing, a tiny vibration, a change in temperature, can mess up the whole calculation and introduce errors. The technical term for this is decoherence, and it is the absolute arch nemesis of quantum computing. So the real holy grail isn't just getting more physical qubits, it's about bundling them together to create a single, perfect, error-corrected logical qubit. This analogy is absolutely perfect. It's the core challenge of quantum error correction. You might need to take hundreds or even thousands of these noisy, fragile physical qubits and weave them together with complex codes just to create one single, reliable logical qubit that you can trust. This is the moonshot problem the entire field is trying to solve right now. But even with a challenge that monumental, just look at the money that's pouring in. These startups are getting valuations in the billions of dollars, numbers that rival what we've seen in the AI boom. Clearly, the smart money is betting that this problem, this challenge of error correction, is going to be solved. And this is why it matters. This is why everyone is racing so hard, because a true, fault-tolerant quantum computer isn't just an academic toy. It's a machine that could change the world. We're talking about designing life-saving new drugs by simulating molecules perfectly, inventing new materials for super-efficient batteries, solving impossible logistics problems, and, yes, breaking a lot of the encryption that keeps our digital world secure today. Look, we are still at the very beginning of this journey. The machines are noisy, the challenges are immense, but that inflection point, it feels like it's really here. The research is moving faster, the investment is pouring in, and the breakthroughs are happening quicker than anyone predicted. So the question is no longer if quantum computing will change our world. The only question now is how and how soon.